Here we are trying to come up with a structure that satisfies a chemical formula that's given. First thing I'm always going to do with a chemical formula like this is to calculate out the degrees of unsaturation. And that's 2 times the number of carbons plus 2 minus the number of hydrogens. Oxygen doesn't factor in, so we can ignore the rest of the formula, all divided by 2. And so we get degrees of unsaturation of 4. So we know now that we have, in some combination, 4 pi bonds and or rings. Now we may also recall that 4 degrees of unsaturation is very, very often a sign of an aromatic ring. And we'll see in a few minutes as we get to our carbon and our proton NMRs whether that's an accurate assessment. But right now we want to start with our IR spectrum. And the first thing I noticed in this IR spectrum is sort of this 3000 to 3500 region is empty. And the reason that's important to me is knowing that we have 2 oxygens in here. That tells us that we're likely to not have any alcohols. The second thing I want to focus on is this region. We can see here the only real significant peaks are down around 1600. So that leads us to a very likely conclusion that there's no carbonyls. So then what types of functional groups could the oxygens be used for? So we know we're unlikely to have an alcohol, and we know we're very unlikely to have a carbonyl. So the logical conclusion at that point is that maybe there's some sort of ether. So let's go down to our proton NMR. And our proton NMR shows us a couple things that are interesting. But probably at least the first thing I notice, is these are all singlets. So there's no splitting in this molecule at all. And so that leads me to believe that we're going to be looking for a fair amount of symmetry in this molecule. Now, based on these 2 peaks here, they're just below 6.5, which is a little on the low side for an aromatic ring, but not out of, completely out of the realm of possibility. So I want to skip down to our carbon NMR and see if the carbon NMR tells us anything about aromaticity. Our carbon NMR clearly shows us we have a group of 4 peaks well within our aromatic region. So at this point I'm going to go back to the proton NMR, and I'm going to make the assumption right now that we have an aromatic ring. Now, the strange piece on this question is the fact that those 2 aromatic proton peaks are both singlets. And that's probably going to lead us to a somewhat unusual splitting pattern. So where else do we have peaks? Well, we have a peak here just below 4 ppm. And we know that's typically an oxygen bonded to a carbon. Now, most likely it's going to be an oxygen bonded to a CH3, given that the chain doesn't have any protons adjacent to it. Also, remember, we only have 9 carbons, 12 hydrogens, and 2 oxygens to use up in this compound. So the idea of an OCH3 there makes a lot of sense. This peak, just above 2 ppm, is characteristic of an aromatic ring attached to most likely a methyl group, again because there's no splitting. Now, if we look at our aromatic ring, that's 6 carbons. We have a 7th carbon from the OCH3 and an 8th carbon from the aromatic CH3. So we're missing 1 carbon. And due to the fact that we've got all this symmetry based on the splitting patterns and the number of peaks, that would indicate to me that we likely need one of these groups repeated. Now there's 2 reasons I'm going to pick the one that I'm going to go with. And I'm going to suggest that there's 2 OCH3 groups. Why? Well, there's 2 oxygens in the molecule and we've only accounted for 1. And also, this peak is significantly larger than the one representing just the methyl attached to the aromatic ring. Now I need to arrange these 3 groups, the 2 methoxys and the 1 methyl, on this aromatic ring so that we get only 2 different hydrogens as well as both of them being singlets. So I'm going to start out by just putting the CH3 here. And if I do this, again, if I need to keep symmetry, the only places that I can put the methoxy groups are here or here. Now if I put them where I've highlighted in red, then those 3 remaining hydrogens are going to be adjacent to each other on the aromatic ring, and we'll end up with splitting patterns. But if I put them here, you'll see that we maintain our symmetry of the ring. The 2 protons that are highlighted, or the 2 carbons that are highlighted in red, they'll be equivalent. They'll also be a singlet. And then we'll get 1 more proton down here at this position, which is also a singlet. And so a slightly unusual looking proton NMR, having all singlets definitely is something that makes this one a little bit more challenging, but there we have our final structure.